So in this video, I want to make a connection here in that you've learned about antiderivatives actually back with the mean value theorem, in that that's one of the consequences of the mean value theorem, is that we're able to do antiderivatives. But antiderivatives also play a role with definite integrals. First off, some function notation that you'll see me using in this video and videos going forward. The function notation that you're used to with lowercase cursive letters to name functions, and derivatives with either Leibniz's form of ratios or the prime notation created by Newton. But then if I want to talk about antiderivatives, you'll see me using capital print letters of that function name. So the function f has an antiderivative that I label capital F. If I had a function g, its antiderivative would be a capital G, and so on. What I want to bring up here is that the way we think of antiderivatives are, if we took the derivative of an antiderivative, we should get the function. And if you think about that, that's how we actually checked our antiderivatives. By saying, oh, I think this is an antiderivative, I'm going to take the derivative to see if I ended up where I started. So in other words, the derivative of the antiderivative is the function. This is actually known as the fundamental theorem of calculus part 1. It seems very basic, but it should be, because it is a fundamental idea for calculus, that taking the derivative of an antiderivative leads me back to a function. But the fundamental theorem actually has a second part, which says that for a definite integral, if I find the antiderivative of the function that I'm integrating, plug in the upper bound, plug in the lower bound, and subtract, that actually gives me the value of the definite integral. And this is how we normally calculate definite integrals, by using antiderivatives, plugging in the two bounds, and subtracting them. The key here is, remember, you're plugging in upper bound, then lower bound, and subtracting. So for example, the integral of 5. Well, if we do the antiderivative of 5, that would be 5x plus c. So if I so when I actually calculate this, I want to take the antiderivative, plug in 2, my upper bound, plug in 0, my lower bound, and subtract those. So when I plug in 2, I get 10 plus c. When I plug in 0, I just get c. And when I subtract those, the c's end up canceling. And what I'm left with is 10. And that is our actual antiderivative, or our actual definite integral value. Now, one thing that's very nice to keep track of here, because we're subtracting two different values of our antiderivative, those c's will always cancel out. So what this means is, for definite integrals only, we can ignore the plus c and actually not even have to write it, because in a definite integral only, the plus c will always cancel out. So some other brief examples here. If I have the integral from -1 to 3 of x with respect to x, the antiderivative of x would be 1/2 x squared. So my integral would be the same as taking 3, plugging it into my antiderivative, plug 1 into my antiderivative, and subtract. And if I did that, plugging in 3 gives me 9/2. Plugging in 1 gives me 1/2. And that's going to equal 8/2, or 4. Now, where I do have to be careful is with antiderivatives, I have to watch for vertical asymptotes. If you remember, vertical asymptotes are not integrable. So I do have to keep an eye out for those. So if I'm looking at the integral from -1 to 1 of 1 over x with respect to x, 1 over x has a vertical asymptote at x equals 0, which means, because 0 is within my bounds here, this does not exist. And if I do this using antiderivatives, well, the antiderivative of 1 over x is the natural log of x. And I can check that because the derivative of natural log is 1 over x. So if I plug in 1 and then subtract plugging in -1, well, plugging in 1 gives me 0. But trying to find the natural log of -1, well, the domain for natural log is x has to be a positive number. So this doesn't exist. So I still get does not exist. However, if I were looking at 1 over x squared, well, this is the integral from -1 to 1 of x to the -2. Again, like with 1 over x, there is a vertical asymptote at x equals 0, so this really does not exist. However, again, if I were to look at antiderivatives, well, the antiderivative of x to the -2 is going to have x to the -1 and -1 in front of that. I can ignore the plus c like you've noticed I've been doing. And if I actually start plugging in numbers to this, of 1 minus capital F of 1 minus capital F of -1, I get -1 minus, oops, sorry, mistake there. I would get a -1 minus 1, which is -2. So according to antiderivatives, it's telling me I should be able to have a value for this definite integral, but because we have a vertical asymptote within our bounds, we know this integral doesn't exist. So just make sure you're watching out for vertical asymptotes.